Hi everyone, welcome to the new tutorial on fluid friction in a pipe. So today I'm going to talk about the losses that may happen while flowing through a pipe. So there may be different types of losses, minor losses and major losses. So in this experiment we'll try to calculate the major losses. So major loss may happen because of the roughness of the pipe, right? So we know that the friction loss is a main cause of roughness, and roughness is because, right, that friction loss, head loss is because of the friction loss, and friction loss is a cause of the roughness of a pipe. So there is no surface in the world that is smooth, right, ideally smooth. So every surface has some kind of roughness factor. So the pipe we use for flowing water, so it has even different types of roughness. Since we need to flow, right, we need to carry water from one place to another, like this way. If we have a long pipe and it is flowing with a velocity v and a q, flow rate is q, then what will happen if we insert piezometer as before that we saw in the Bernoulli's principle, right, and in even Venturi meter we saw that if we insert any piezometer, so what will happen, what will be here, and if we insert another piezometer at a length L, so we'll have another height here. So these are the head at that point or at that section. So if we just see, these heads are not same because we have head difference, right? So that's the difference, it is called head loss. So why is the difference? Because of the roughness, right? We have roughness on the wall of the pipe. So because of that roughness we are losing the head, right, the energy, we are losing the energy of the water. We are not losing the total amount of water, but we are losing the force of water, the pressure of water, so energy of water. So that is the problem. So if you want to distribute water, right, for your city or for any rural area, whatever you have, so you have an overhead tank, right, big overhead tank, this one, and you want to distribute water like 100 miles or 50 miles away. So then what you'll do, for 20 miles away you have to have the minimum head. You will calculate what minimum head you need to distribute water to the households. That's why you have to be able to calculate the minimum head, and you have to make sure that the people who are living there, who are gonna use the water from your distribution system, they will get that pressure, that head, when they open their tap, right, when they use the tap water, they will have that minimum head. Then they can use the water from the supply system, otherwise they won't be able to utilize the water. So that's why you have to be able to supply that head. You have to make sure that you have the head there. And if you won't be able to calculate the head loss while carrying the water, right, from 20 miles away, so then what will happen? The minimum head that you calculated, or the design head, people won't get that head there because of that head loss, and that head loss is because of that roughness of the pipe. So we have to be able to calculate the roughness. So in this experiment we will see that. So that is the roughness. So when the flow increases, flow rate increases, then the velocity will also be increased. So what will happen, the flow will be more turbulent. Then the relationship in between the head loss and the velocity of flow is different. So what will happen, that's why we have to consider here what type of flow it is. Is it laminar flow, or it is in transitional state, or is it turbulent? So that's why we'll divide, because we know the flow may be in two different types, either in laminar and or in turbulent states. Most of the flow in pipe and rivers, they are in turbulent flow, in turbulent state. These are the states of flow. So we'll calculate Reynolds number. So when the flow is laminar, right, when the flow is laminar means Re, this Re should be less than 2000. What is Re? Re is nothing but Vd divided by nu. V is the velocity. For example, we are going to calculate R. What is the Reynolds number here? So we need the velocity V here, we need the diameter D at that location, and we need the kinematic viscosity nu for that temperature, because it depends on the temperature. That's why we need that kinematic viscosity. Then we'll be able to calculate the value of Re, and if the value of Re is less than 2000, then it is a number that determines whether the flow is laminar, transitional, or turbulent flow. If it is less than 2000, then it is a laminar flow, and when the flow is laminar, then the relationship between head loss, this head loss, is directly proportional to the velocity. So then it's this. But if you increase the flow rate, then velocity will be increased, because we know the Q is equal to AV, keeping the cross-sectional area same for the same pipe diameter. If you increase the flow rate, definitely velocity will be increased, and when the velocity will be increased, then the relationship will change. If velocity increases, this velocity increases keeping diameter same, the Reynolds number will increase, right? It also will increase. Then what will happen? When the Reynolds number will exceed 4000, is greater than 4000, then the flow will be turbulent, because the streamline will won't be parallel. It won't be parallel to each other anymore. It will be turbulent flow. Then the relationship head loss and V is not proportional anymore. Yeah, it is proportional, but it has a power term n this way. The value of n is 1.7522. It depends on the range, right? When the turbulent range is minimum, means when the value of Re is close to 4000, then it will be 1.75, and when it is greater than 4000 and it will increase, then it will be 2. So that means the value HL is equal to K V to the power n. We can use K is the constant of proportionality. We know that, right? If you want to replace any proportionality value, we need to use a constant, so K. So we'll calculate the value of K and value of N. So this value of N should be in between 1.75 to 2. So that is the condition. So when the flow is turbulent, we have the relationship in between head loss and velocity. So in this experiment, that's why we are going to calculate the head loss. So that's why we are just relating the head loss with the velocity. We'll check if the flow is laminar, then we have different equation. If we have the Reynolds number greater than 4000, then we'll have different, right? It will be like this. We have to be able to use this equation. So these are the major equation we'll use in this experiment. So fluid friction in a pipe, because of the roughness, and roughness comes from the distribution of the rough surface. If we have a pipe and the roughness is this, so friction factor depends on the distribution and the size and the shape. It may be triangular, it may be rectangular, it may be spike. So the size, distribution, and the shape of the surface, of the roughness. So it will depend, and we call this roughness as a factor called F roughness factor. So this factor is also, right, it depends, this factor also depends, it depends on different flow regime, whether it is turbulent or laminar. If it is laminar, we have different formula, right, of F that relates with the velocity and other factor, and this one. So in the experimental setup, so what is the practical application? The practical application of this fluid friction is that since it is a major loss, in order to distribute water to a distribution system or any household or any industrial area, you have to know the head loss in order to make sure that the minimum head is there, right? If you want to use a long pipe, then you need to use, right, steel pipe or cast iron, or even for sewage system you have to use that concrete pipe. So you have to know what is the value of the roughness factor, because in the equation we have the roughness factor. So if you know the roughness factor, if you know how to calculate that roughness factor, that we'll do today, and then you will understand that, okay, this is how we can calculate, and then you can calculate the value of head loss, because the main purpose of this experiment is to calculate head loss by understanding the logic behind the calculation. That's why we'll calculate the Reynolds number to make sure the state of the flow. Once it is laminar or turbulent, based on that information, we'll use that type of equation because we have separate equation, because the relationship is separate for laminar and for turbulent flow as well. So this is the experimental setup. We will have a tank or a circular pipe, and then we have other smaller pipe, and we will allow water to flow through these pipes, and we have different scales that will measure the head difference, because the same setup we saw here, it will be something like that, right? It will be something, it is just representing this thing, but that is the vertical. We have one pipe that is vertical, and we are attaching different piezometer or a smaller pipe, and we'll measure that pressure, and based on that one we'll calculate the head loss directly, right? But that, because the pipe is big, so if we use any kind of water manometer or any kind of water piezometer, then it will be bigger, so we won't be able to cover that one. That's why what we'll use mercury manometer, or mercury manometer will give you the value of pressure, but when the reading is less, like 1 centimeter, it will measure the height of 13.6 centimeter of water, because mercury is 13.6 times heavier than water. Why do we know that? So the specific gravity of mercury, that, so we'll use that information as well. So that is the representation of the experiment. We'll measure head loss, and from that head loss we'll know the diameter of the pipe, and we'll calculate the velocity, and then we'll be able to calibrate the system. Okay, so that's that. And let me just derive the equation. When the flow is laminar, then we have a set of equation. But in the previous experiment, what other people has done, right? Other people have done, so they even calculated, because these are the empirical equation, right? Empirical. This is the empirical equation, means all this formula we are giving here, this is not from all from derivation or all from theory. This is basically based on experiment and experience as well. That's why these are called empirical formula or equation. So Darcy-Weisbach formula. So Darcy-Weisbach formula relates friction factor with head loss, with pipe diameter, and the head loss or the velocity head as well. So if we want to relate head loss is equal to nothing but 4f, and then it is L divided by D V square divided by 2g. So from Darcy-Weisbach formula we can see that F is the friction factor. Friction factor is directly proportional to the head loss, right? If friction factor increases, means roughness increases, head loss will also be increased. If the length of the pipe is increasing, means if the length of the pipe increases, that means we will have more frictional surface, the head loss will also be increased. And the diameter, if the diameter of the pipe is bigger than smaller, then what will happen? The water will face less restriction, then head loss will decrease, it will be reduced. And for velocity, if you increase the velocity, means if you reduce the diameter, definitely water will flow very fast, right? And then the velocity head will increase, and if the velocity head will increase, the head loss will also be increased. So that is the relationship. So from that relationship, if you somehow calculate the head loss from that setup, you can calculate F, right, by reversing that equation. So what will happen? That, right, you can just reverse it. So we have that 2g divided by v squared, it will be just reversed, and you will have like HL, and then you will have the value of D, and you will have 4, and you will have L. So from this equation, if you know the length of the pipe, definitely we'll know, or experiment setup, we have a limited length of the pipe, and we know the diameter, we'll calculate HL from the experimental setup when we'll use 2 piezometer at 2 different locations, and we'll calculate the velocity because we'll know the flow rate, right? If you know Q, we know Q is equal to AV. Since we know the diameter of the pipe, we can calculate pi divided by 4 d squared, and then we can calculate V. From this V, we'll be able to calculate the friction factor for that specific pipe, right? And when we have the friction factor, right, when we have the friction factor, there is another empirical relationship in between the friction factor and the Reynolds value, because we know the Reynolds number is equal to Vd divided by nu. It also relates, right, the velocity and the diameter of the pipe. It is called characteristics length, and for any pipe, diameter is the length. Basically, the Reynolds equation VL divided by nu. When it is pipe, then it is the diameter we use. There is another empirical relationship. It is 0.079 Re to the power minus 0.25. So that is another relationship in between Reynolds number and friction factor. Somehow, if you know the Reynolds number from this information, if you know the diameter, if you know the velocity of a pipe, and if you know the viscosity for that specific room temperature, then you can calculate the friction factor. Our objective is to calculate friction factor somehow. If you want to use that formula, you have to know velocity, you have to know head loss, but for this one you don't need to know head loss. We only need to know the diameter of the pipe. That will be easy, right, to know, and the velocity. But for this experiment, you have to know the length of the pipe, you have to know the diameter of the pipe, and also the head loss and the velocity as well. So yeah, we'll decide which equation we'll use for engineering design. So that's why people just conduct different types of experiment, and they have this type of empirical relationship. So if the flow is in laminar range, means the Reynolds number is less than 2000, flow is laminar, so we can't be, it's not possible to use, and it's not even accurate to use that same equation that we can use for turbulent flow. That's why we have different relationship for a Reynolds number, and we have another formula for laminar flow, right, when Re is less than 2000 for pipe flow, and the range is different for open channel flow. We'll talk about that one later on. This is called Hazen-Poiseuille equation. Okay, Hazen-Poiseuille equation. So it is also relating that head loss with friction factor, and then LV, and then rho g V in rho g d squared. Okay, rho g d squared. So 32 mu LV rho g d squared. So here that mu is called dynamic viscosity. It is dynamic viscosity. Okay, so if you know that mu, and if you want to know nu, so it is mu divided by rho. That is called kinematic viscosity. Kinematic viscosity. So that's why if you want to know, and we can replace that value, right? So 32, and we can replace mu divided by rho, because we have mu here and we have rho here, and we can use that nu LV divided by g d square. We can use even that one. So at first we'll check if the flow is laminar or turbulent. If it is laminar, we'll use that Hazen-Poiseuille equation. If it is turbulent, we'll use Darcy-Weisbach equation, or you can use that empirical equation, F is equal to 0.079 and Re to the power minus 0.25. So we have another relationship from this one. If the flow is laminar, 16 divided by Re. So that relationship, we have another similar relationship for laminar flow as well, 16 divided by Re. So therefore, what we can see for turbulent flow, we have that relationship 0.079 Re to the power minus 0.25, and here is F to the power 16 divided by Re. So the F is a function of Reynolds number. That is pretty sure, right? It's a function of Reynolds number. So we can generalize the formula like this way: F is equal to C R to the power m, right? So we are just generalizing this formula, that okay, we have this form, we will have a constant in front of Re, and the power of Re will be m. We don't know the value of m yet, so we'll conduct our experiment for different setup. We'll calculate the values of Re, and we'll calculate the friction factor, and then what we'll do, we will use our log graph paper as before, because we are dealing with the same type of formula for a long time. C raised to the power n. See, it is the same formula, right? So we'll plot in a log graph paper, and then we'll calculate the exponent from the slope of the line, and using the point from the graph we'll calculate the value of C as well. So this is how we'll proceed our experiment. Okay, so these are the equation, it is there, and what we can do, so that is the objective for today, to find the frictional loss HL. We can calculate that one from the difference, and to plot that HL versus velocity in a log graph paper, and we can calibrate that formula as well. This one we mentioned that right at the beginning, that HL is equal to kV to the power n, because we know that HL is proportional to Vn when the flow is turbulent. So HL is equal to kV to the power n. We'll calculate that one, and the value of n is 1.7522, and then we'll plot that F. So we just saw the relationship as F is equal to C RE to the power m. We'll even plot this one. So today we'll have two log graph paper, and then you can plot that head loss versus velocity for turbulent graph paper. It will be like a straight line. It is pretty simple. If you plot that, it is not a problem, right? So here you can see what are the factors upon which, okay, let me just quickly finish that part first as before, then it will be easy to answer the question, right? So the diameter of the pipe, if you have any slide calipers and if you have a section of the pipe, you can easily calculate the diameter of the pipe. What will be the diameter of the pipe? Is it external or internal? Definitely, since the water is flowing through the pipe, you have to be able to calculate the internal diameter of the pipe. That is for sure. So you have to use the upper part of the slide calipers that can measure the internal diameter of the pipe, right? So from the left section, you can ask your instructor, or your instructor will show that how to measure that one. And if you have any previous experience from your high school level, then you have the experience as well. So you can, we have that diameter of the pipe. Once we have the diameter of the pipe, we can apply the formula, right? Pi divided by 4 and d square. So we know that the diameter of the pipe is that, so pi 3.1416 divided by 4 multiplied by 1.69 and a square. So it is giving us 2.243 centimeter square. Okay, and the temperature, you have thermometer there, so from that we need the temperature, because we are gonna read the value of viscosity from the table. It is given in the book, right? We can calculate that. So we are calculating that value from book mu, and we are calculating nu as well, and it is also given there. If you know the temperature at that if you know the density at that temperature, you can calculate mu and nu. Even you can read directly from the table from your book, and we calculated everything. We have the density in terms of gram per centimeter, we have this dynamic viscosity mu, and then we have kinematic viscosity as well. So we have this volume, we'll measure the volume in terms of a liter, right? So if we have, so we have 10 liter, 10 liter is equal to, if you multiply it by 1000, you will have centimeter cube. So that's why, yeah, we have 10 liter, so 10 into 10 to the power 3 is equal to 10 to the power 4 centimeter cube, right? We have 10 liter water. 10 liter water is equal to 10 into 10 to the power 3 centimeter cube, means 10 to the power 4. Okay, and the time is this as before, and we calculated the Q. Yeah, you'll get the Q directly from the experiment. It is there. We have the Q, right? How can we measure that? As before, we have 10 to the power 4 divided by 13.56. We have 10 to the power 4 divided by 13.56, right? So we have 7. We have 737.46. Yeah, if you divide this by t, then you are getting this one. And what is the velocity? Velocity will be nothing but q is equal to av, and v is equal to q, means 737.46 and divided by the area, right? What is the area? 2.243. 2.243, because we know the pipe is like this. We know the diameter, water is flowing through this pipe. Okay, that is the diameter D. So this divided by 2.243 is huge because it is friction. The water, the velocity is too fast, to 328.78. This is centimeter per second, means 3.28 meter per second. So it is 328.78. This is centimeter per second, and we have to calculate the Reynolds number. We know the Reynolds number, the equation is RE and VD divided by nu. So what is the velocity we just saw, right? Is 328.78, and what is the diameter? 1.69 centimeter. Everything will be in centimeter. And what is the value of nu, right? We calculated the value of nu, 0.00847. So 0.00847 centimeter square. Yes, that is the unit, centimeter square per second. So we have this velocity multiplied by 1.63 and divided by 0.00847. So what we have, it is huge, right? It is a 63,272. So that is the number. It doesn't have any unit, so it's definitely a turbulent flow. So from that experiment, we calculated the head loss directly from that setup. The difference between these two piezometer, we have this 12 is height is mercury manometer, right? So that's why we have to convert it to height of water. How can I do that? So we know that the specific gravity S is equal to 13.6 for mercury, right? Hg. And what we have to do, if we want to convert that depth of water to mercury depth of, the height of mercury to the depth of water, we have to use S minus 1 multiplied by the height of that Hg. Then we'll get H2O, right? We'll get the height in terms of the water. So S is 13.6 minus 1 multiplied by that 12. We have 12 centimeter, right? It is there, 12. So 12 into multiplied by 13.6. It is nothing but 163.2. So we have that, and yeah. So that is the information you can do, and there will be other calculation. You can even finish that one as well, right? So that is that. But the problem we have, we consider the temperature 27 degree. That's why we need to even, it is better to even make correction for that density as well. So what we have to do, we have to divide this value by the density of the water. Then it will be easier to calculate, right? Or you can, before, we basically divide this way, then it will be reduced a little bit like this way. I'm just showing, we don't need to do that because it is not that so we have to divide 0.99. what is the value of this one? 996, 0.996. So 13.6 divided by 0.996, this minus 1, if we have this, and if you multiply by 12, then what we'll have? You'll have 151.85. Okay, we can keep that because we have this value here. Okay, we can use that correction as well, no problem. You can use that because it is a matter of temperature and we are just trying to make accurate calculation. Okay, so once we have that for each of this group, so we have 151.88, and what will be the value of F? So now we have to calculate the value of F using that Darcy-Weisbach formula, because we need F, right, for each of this group. So we know F, what we wrote previously, the value of F is, it is 4D if I just arrange it this way, I have not 4D, this D divided by 4L, I have that there. You don't need to memorize that one, or you can use that, and you have 2G divided by V square and HL. Okay, so D we know 1.69, and we have 4, and let me check the length of the pipe. What is the length of the pipe we used for this experiment? Do we have that here in the data sheet? It is not there. Let me just it is 4. The length is pretty big for that experiment we use. It is 4 meter. The length was L was 4 meter, means not 4 meter, it was 1 meter. Oh, it is 1 meter, not 4 meter. It is 1 meter. Okay, it is 1 meter, 100 centimeter. So we have to multiply by 100, and we have 2 into 981. We have the velocity 328.78, 328.78, and you have to square it, and we have the head loss 151.88. Let me check the value of the friction factor. We have this 151, that one, into 2 into 981, okay, divided by 328.78 square, and into 1.69 divided by 400. Okay, so what we are gonna get, we are getting here 0.01164. okay, 1164. So that is the value of the F. So we are repeating this experiment for other conditions, other groups. We are changing the flow rate. We are getting this flow rate for 5 different groups. We are calculating the velocity, we are calculating the Reynolds number, we are calculating the head loss and friction factor as well. And then we need to calibrate those equations, right? What are the equations we have? We have that head loss is equal to K and V to the power N, and we have another equation, friction factor C and RE to the power M. So we have to plot velocity and head loss, Reynolds number and friction factor. So here is the plot. You can see we plotted velocity and we plotted that head loss, and we are getting that value. So the value of N for this equation will be, so it is HL is equal to K V to the power N. So N should be 1.7522, right, 2.0. So I have plotted that one. I quickly plotted this one. Let me check if I can, if I can read the value as before. So I can select one point. I don't have any specific point for this one. I can select this point. It looks like in the middle of that, right? So it looks like in the middle of that. So if I select this point, I have 1, and then I can directly read from here the first. That will be the second point, and I can select another point from where? From this one, okay? From this one. So that will be that value, and maybe let me see if I can draw another one. It is this. The first point is this is 100, so that will be 200, right? So the value is 200, and the corresponding value of head loss is 10, 11, 12, 13, 14, so 14.2, maybe 14 not 14, it is 10, 20, 30, 40, right? 20, 30, 40, 50, 52, 200 and 52. Similarly from this one we have 100, 200, 300, 400, 500. So we have 500, and from this one we have this value. What will be the value? That 100, 200, 300. So that will be 300. Okay, so 200 and 300. So what will be the value of N? Again log. So for this case the value of 52 divided by 300, and the value of 200 divided by 500. Let me check what will be the value of that. Log 52 divided by 300 divided by log 200 divided by 500. I'm not sure what is getting. Yeah, I got 1.912. It's pretty good, right? It should be in between 1.75 to 2. So the head loss, so the HL is equal to C and V to the power 1.912. If I use the first point as what is the head loss, now we have, right, what is the head loss? 52, right? 52 is equal to C is unknown, the velocity is 200 to the power 1.92. So 200 to the power 1.92 and 52 divided by that. So we have 2.065 into 10 to the power minus 3. So that is the value of C. So what we have the relationship HL is equal to 2.065 10 to the power minus 3 and V to the power 1.912. So that is the empirical relationship we have. And if we plot again the Reynolds number, right, along x-axis and the friction factor F along y-axis, we have very flat line, but still it is that. So I just tried to plot an average line following, right, we have some points on the right side, I have some point on the left side. I don't know if it is accurate or not, but I tried quickly. Let me check, let me just quickly calculate the value, because now we have F, right? So for this one we have F is equal to C RE to the power M. We have to calculate the value of M. So what I can do, I can select this point, it looks like in the middle of that line, right? And I can even select that point. So this is 10,000, 20, 30, 40. So this should be 35,000, right? And what will be the value? It is 0.01. The first point is 35. These are the Reynolds number. Corresponding friction factor is 0.01. We need another point. So I'm gonna use so that is pretty difficult if you don't have any point on the line. Okay, let me use that point. Okay, maybe that will give you that value, but let me make it sure that it's gonna happen that way. Okay, so that will be measuring that one. If I wanna remove this one again, if you wanna remove this, and let me just quickly draw that. Let me quickly draw that. Okay, let me quickly draw that. So I don't know how can I read that value, but you have to estimate that is 0.01. So that is 0.02. So it will be something like this is 0.015. So that is maybe 0.01, 0.011, 0.012, 0.013. So consider that is 0.013. Okay, so that is 100,000. Okay, you have 100,000, 0.013. Let me calculate the slope M. M will be a log 0.01 divided by 0.013 and divided by log what will be the value? 3500 divided by what? 3500 divided by 100,000. Okay, then what will happen? Log 0.01 divided by 0.013 divided by log 35,000 divided by 100,000. It's really big calculation. So I have 0.249. That is the value I have. It is pretty close to that point, minus 0.25. It is this. So from this calculation I can calculate the value of C, right? That C. So we have F, I can use friction factor 0.01. This one is equal to C. R, I can use that 35,000 to the power 0.2499. So 35,000 to the power 0.299 and 0.01 divided by that value. I'm getting C. C is 7.317, 10 to the power minus 4. So that is the value we have. F is equal to 7.317, 10 to the power minus 4, and RE to the power 0.2499. So that is the relationship in between these two values. So we are done with this one. You can plot the third one. It will be only nothing but a line. So these are the calculation we can make for friction factor, right? So let me try to answer the question we may have. So what are the factors upon which the frictional loss in a pipe depends? It is nothing but that roughness, right? Size of the roughness, shape of the roughness, and density of the roughness, and distribution of the roughness. That is the cause of head loss. And what is meant by critical Reynolds number? I just mentioned that if the Reynolds number is greater than 2000, the flow will be laminar. Less than 2000, the flow will be laminar. If it is greater than 4000, then flow will be turbulent. In between this range, it will be transitional. So these are the critical Reynolds number, right? Upper critical, and that is the lower critical. So what is a higher and lower critical point? So these are the higher and lower critical point. Higher critical point, lower critical point, right? So write down the different types of losses that may occur in a pipe flow. So what type of loss may happen? We may have this type of sudden contraction. We may have sudden expansion. So if flow occurs from left to right, and we may have this type of elbow bend. We may have this type of bend. So because of the fittings and settings and shape of the pipe, right? So there will be minor loss. These are called minor loss. And the major loss is the head loss because of the friction factor and the roughness of the pipe or the surface over which flow is occurring. So these are the cause. And there is another final mathematics we have, and while it is not water, it's while the specific gravity is given there 0.85, we have to calculate the value of, right? So the viscosity is given there, flow is in meter, the flow the water flows in a, that well flows in a 10 centimeter diameter pipe, means D is equal to 0.1 meter. It is in meter square, so I'm calculating in terms of meter. And the this liter, the Q is in 0.5 liter per second. From liter to meter, if you want to convert, 1000 liter is equal to 1 meter cube. So you have to divide this by 1000, then you will have meter cube per second. So 0.5 into 10 to the power minus 3 will be the value. Okay, so you have to check if the flow is laminar or turbulent. For checking this one, you need that Vd by nu. So nu is given, that is the nu, and d is also given, right? So what is the d? 0.1, and you have to know the velocity v, and nu is given, right? 1.8 into 10 to the power minus 5. So in order to calculate the value of v, this flow is given. So q is equal to AV. So V is equal to Q divided by A, and in order to calculate the value of A, the diameter is given 0.1 square. So what will be the velocity V? Let me calculate 3.1416 divided by 4 multiplied by 0.1 and squared. So 0.5 into 10 to the power minus 3, this will be divided by the previous value. So the velocity is 0.063 that meter per second. So what will be the value of Reynolds number? Okay, so 0.1 into 0.063 divided by 1.8 into 10 to the power minus 5. So this one into 0.1 divided by 1.8 and 10 to the power minus 5. So it is 353. See, It is 353.67. We can round 354. So the Reynolds number is 354, definitely less than 2000. So the flow is not even turbulent, it is laminar flow. Okay, so this is how, if we have any information about the viscosity, we can calculate the viscosity from temperature, and we can calculate the friction factor and roughness. Anything we need, we can easily calculate, and we can decide whether the flow is turbulent or laminar. Okay, so this is how we can do that. So I think I'm done with this experiment, and definitely, yeah, we have one experiment left. In the last experiment we will see a flow head loss because of that minor losses because of feeding and seeding. We'll do that, we'll calculate everything. So in this experiment, what we have learned today, so we know that the major loss is because of the friction factor, and friction factor causes because of the roughness of the pipe, and it depends on the distribution of the roughness, size of the roughness, shape of the roughness, and density of the roughness. Once we have the roughness, we can calculate the Reynolds number by understanding or by calculating the values of the characteristic length, which is the diameter for a pipe, and then the viscosity and the velocity if you know the flow rate. Once we know the flow is laminar or turbulent, and based on that information we can calculate the value of friction factor. If it is turbulent, we can use the Darcy-Weisbach formula, and if it is laminar, we can use Hazen-Poiseuille formula, right? And once we have that, we can calculate the head loss. Once we know the head loss, we can design our water distribution system. We have to be able to design water distribution system, otherwise you have to apply your engineering knowledge. So that is engineering. All these equations, these are basically based on experiment and experience of previous people. So that's why we are calling this equation as empirical equation. So that is the experiment is all about. So that's it. I'm not gonna extend the video length, so I'm gonna finish here. So if you have any query, and if you have any comment, any question, you can ask your instructor how to take readings from the setup. So it is not possible right now to display the setup here. That's why I just always try to show the image of the setup, and I can collect the data, and then in the laboratory section you can use your own hand to take the readings. Then you'll understand what is actually happening. Okay, so that's that, and I'm gonna finish it here. So thank you very much for watching these videos, and okay, in the next tutorial we'll finish our entire course. So until then, stay safe and take care.